This is Math331, lecture, let's say, 16. What we're going to do is continue today on the Pigeonhole Principle, the Box Principle, and then start talking about some applications of it. And then there was a request to do some mathematics related to, is there such a thing as a hot hand, a lucky batter, a hot streak? And depending on which paper you read, the answer is no. Or yes. And so it's always nice when you have a difference of opinion in the scientific community, which argument you consider convincing. Who is a Red Sox fan here? This is a chance back. Okay. Who is the greatest clutch hitter of all time? David Ortiz. Right. Excellent answer. Now the question is David Ortiz really a clutch hitter? If you look at his performance, the answer is yes. However, if you look at enough people, how many people would you expect to be clutch hitters if people are just hitting randomly? And then in enough clutch situations, certain people just by randomness will turn out to look good. David Ortiz is, of course, different. He's a clutch hitter. But if you have enough people, you will have some people who will look like clutch hitters just because of law of probability. What else will you have? Yes, you'll have people who look like, Alex Rodriguez, Mr. March, Mr. April. Although I think he finally did have one good playoff series towards the end. But just with enough people and enough instances, you will have situations where you would tend to think, this person is doing really, really well, this person is doing really, really poorly. And it could just be randomness. I'll give some examples of this going back to the 2008 presidential election, if time permits. All right. So do we all understand the box principle? If you have n+1 pigeons and n boxes and you shoot you carefully place the pigeons in the boxes, at least one box gets two pigeons. The more general principle is that at least one box has to have at least the average number. Everything can't be below the average. This is very similar to the mean value thing that we did before. Okay, this is not surprising. So here's a nice fact. Let's let I be the set of numbers 1, 2, without 2n, and S will be a subset of I such that the cardinality of S is equal to n+1. Prove there exists A and B in S such that A divides B. Okay. What do you think might be useful to prove this? Any thoughts on what might be useful? Probably Pigeonhole Principle, as we just started off today's lecture with Pigeonhole Principle. So when you're doing Pigeonhole Principles, you need to do two things. What are the pigeons? And what are the boxes? Typically, it's easier to figure out what the pigeons are. These are the objects where you have a certain number of them. What do you think the pigeons are here?
Items in S.
Yeah. It's the X and S. The boxes, that's the hard part. So this is very similar to the monovariance. This is the art part of the class. Think of it as the quadratic formula, the ratio test, the root test. These are mechanical procedures we can just grind through. It's really not that challenging to do the quadratic formula. Maybe seeing how to prove the quadratic formula, sure. Do people know about the cubic formula? There is a formula to solve the cube. What I heard is that in the old days, you could actually challenge people for their math position, and the person who discovered the formula for the roots of a cubic kept that in reserve, so that whenever somebody challenged him, he could always just respond with, find the roots of these 10 polynomials that are cubes. And then that way he's safe. The publish or perish system we have now has some disadvantages, but it does at least get results out into the literature. There is a formula for the quartic. There is not a closed form expression for the quintic or higher. This is one of the great results you'll learn probably in Galois theory, maybe abstract algebra. Okay? But for things like the quadratic formula, ratio, root test, it's mechanical. It's really hard not to get those problems right. For these problems, it's much harder. You have to figure out what the boxes are.
Why
Now, bless you. Sometimes you can attack a problem like this by doing special cases. It's painful. What would be your first special case? And I don't advise doing this, but special case. What would be the simplest case? Yes?
If it includes 1.
Yes. 1 is in S, trivial. Right? Any other element will work. Oh, I guess technically I should say something about A and B. It's implied. They're not equal. All right. If A equals B, this is really not that difficult of a result. And we probably don't need S to have n plus 1 elements. So if 1 is in S, it's trivial. So case 2, 1 is not in S. And what might you want to assume is in S? Yes.
2.
Yeah. Now, sometimes, even though this is not a good way to prove the problem, it's not bad to play with special cases. What could you learn by playing with special cases? What might they give you insight in choosing? Your boxes. So if 2 is in S, what can we deduce? So you might even have to break this into subcases. I mean, that's the only thing better than doing things into cases. Yes?
If there is an even number, then 2 will divide.
If there exists an even B in S, we're done. Therefore, all other elements are odd. And they can't be 1, because we know 1 is not in it. So it must be 3, 5, 7, 2n minus 1. Yes?
And that doesn't have enough cardinality.
It doesn't have enough cardinality? Okay, so one thing is it doesn't have enough cardinality. So contradiction. Or
3 and 9.
Or 3 and 9. But then we need to be at least large enough to have 3 and 9. So it's safer to say it doesn't have enough cardinality. So too small. Or if n is big, 3 divides 9. So this is one way to start proceeding. Then we could say, well, let's assume 1 and 2 are not an S. And to me, this is starting to get painful. But maybe we can get some idea of what might be good boxes here. So one issue was that we didn't have enough elements. But what was the other issue? We had 3 divides 9. So any thoughts on what we should choose for our boxes?
Things divisible by 2, and things divisible by 3.
So one thing is we could try to make our boxes divisible by 2, divisible by 3. If we do boxes divisible by 2, how many boxes do we have? I'm sorry?
N.
We would have... So is each even number a different box?
No.
So we're just doing like evens and odds? Because remember, if I have 16 and 24, 16 doesn't divide 24, so 2 things in that box. This is the challenge. The first thing is, if you want, before we even choose the boxes, what if we didn't have n plus 1 elements? Whenever you look at a problem, you want to learn how to read a math competition problem. If you see the number 2018 on the Putnam this year, probably doesn't really matter. Last year I think was a good year because 2017 is, I think it's prime. Okay, and so it could be that maybe if you see 2017, all that matters is it's a prime number, not that it's actually 2017. So for something like this, if I would actually give you numbers rather than 2 and I could give you 151. You always want to ask what's the relative size or scale between the 2 numbers. Do you think the n plus 1 is sharp? What would happen if I didn't have n plus 1?
seems like you can fill it up with n elements, and then adding the n plus 1 breaks it.
Yeah, so what n elements would you choose? The last n. So note, need n plus 1. And we could consider just n plus 1, n plus 2, all the way down to 2n. And again, sometimes this helps you get a sense of how to find your boxes. If they tell you you need n plus 1 objects, almost surely n objects will fail. Go back to the circle arc problem we did, where you needed a certain number of points. Almost surely if the points is below that threshold, it's not going to work. Sometimes you can still do it with a lower number, but the proof is significantly harder. So over here, we at least know now that we have to have n plus 1 points. That if we have only n points, it's definitely going to fail. It might fail with n plus 1 points, but we need at least n plus 1 points. We need to find a good choice of boxes. So one possibility was to do even odd. So if you do even odd, you would have 2 boxes. And then since you have n plus 1 elements, at least one box would have more than n halves elements. Is that going to be enough? So what was nice over here? How did we get a contradiction, assuming not just about the size, but we found 3 divided n. So we had 2 odd numbers where one odd number divided another. The boxes is the odd parts. So if I give you a number x, I can write any x as 2 to the m times 2y plus 1, where this is the even part, and this is the odd part. So this is just a really nice decomposition of any number. You can write it as an even and an odd. How many odd parts are there if I look at the numbers from 1 to 2n? So how many possible odd parts are there? I'm sorry? How many odd parts are there? N. There's n odd numbers from 1 to 2n. So this was the challenge. It's finding the right box. There are n odds from 1 to 2n. If there are n odds from 1 to 2n, and these are our boxes, what do we know?
If you have n plus 1, then you have to have at least 1.
I'm sorry?
If you have n plus 1, then you have to have at least 1 even.
One box or one odd
Not
box
quite.
has to be repeated.
One odd box must be repeated. If each odd box only had one element of s, then that would only account for n elements of s. So at least one odd box has 2 elements. So we can write it as, 2 to the m1, 2y plus 1, and 2 to the m2, 2y plus 1. And if we call this one A and this one B, without loss of generality, m1 to be less than m2, now A divides B. And that proves the result. So the challenge here, again, it's finding what you want to do for the boxes. That if I have 2 numbers, the even part's actually pretty nice. Because your even part is going to just be some power of 2. And so for those of you who are enjoying the baseball score challenge, I'll email it later today. the one for the Red Sox score today is a huge power of 2 homage. So it makes sense to go to a problem like this for today's lecture. Once you have this, it's not so bad once you see, okay, I've got n odds, and I've got n plus 1 things, so one box must have 2 things. And then that's going to give me my decomposition. But this is the hard part. This is really more of an art. It's trying to figure out what are the right boxes to do. Okay. Any questions on this? All right, so what I want to do now is I want to do an application. I don't think we've proven how well you can approximate irrationals by rationals in this class. Is that correct? We have not done it, correct? Okay. This is one of the most important things we can do. Who here is in computer science? Okay. A lot of hands went up. Outstanding. What are you allowed to work with in computer science?
Floating points.
Powers of 2.
Powers of 2. Basically, you can work with zeros and ones. You can work with rational numbers, numbers that are essentially coming from powers of 2. That's it. Can you work with a number like square root of 2 or pi directly?
You can like drill it into the hardware, maybe.
You can estimate. But everything has to be done with zeros and ones. So we want to talk about how do we approximate an irrational with a rational, and how do we get a good approximation. There's a beautiful theory called the theory of continued fractions, which actually leads you to the best approximation of irrationals by rationals. And the question is, how do you measure a good approximation? Typically, the rule is the size of the denominator. If you want to get a really good approximation of pi, well, calculate a huge number of decimal digits and do like 3.1415 divided by 1. And if you just take enough decimal digits and divide by 1 with enough zeros, then you're going to get a really good approximation. But that's expensive. So we measure the cost of an approximation by the size of the denominator. So the larger the denominator is, the more expensive. Well, that makes sense, because the larger the denominator, the more computation it takes to work with it. So what we want to do is we want really good small approximations. So what's a really good rational approximation to pi? 3. Right? Now, there are some places that have legislated
It's in the Bible, yeah.
4. What should you do if you're in a land where pi is legislated as 4?
Leave.
No.
Become some profession that requires you to use pi and then use 3.
Overthrow the government.
What's the area of this plot?
1.
So what I'm going to do is I'm going to pay so much per square foot. I will sell this middle back to someone, and then I'll sell these parts, and then I'll sell these parts. So I will buy in squares and sell in circles. What will I do? Oh yeah, I'll make money. And in fact, I could maybe even try to sell the square directly by saying, well, we can calculate the area of the square by approximating with circles. I'm going to give you a discount. I'm going to stop calculating after the third order. And just use that as a quick approximation.
What places?
I think there was a place in Indiana that temporarily had pi was 4. You can do some Google search.
Oh, I thought they made it 3.
No, there are places that have made pi 3, and you can defend that. You cannot defend 4. But if someone is going to do 4, by all means. Now, for one of your homeworks, that's due on not next Monday, but the Monday after, I want you to tell me which is larger, either the pi or pi to the e. This is not due for a while, but I want you to do this without any calculators. No slide rules, no abaci, no computations, other than just theory. Can you theoretically derive which is larger, either the pi or pi to the e? Okay. There's a couple of ways to do this elementarily. There are some ways to do this using some calculus knowledge. Can you just approximate and see which one is bigger and why? And then if there is interest in stuff like this, I will talk to you about the applications for computer science over the fact that 3 minus e is less than 2 minus e. This has incredible applications for computer science. Anybody seen these applications? Okay, so I will show you, in fact, a tremendous application. As a result, I will be able to prove that 2.5 is less than e is less than 3. And this has applications in computer science. So every now and then theoretical math is useful. Right? If you are in computer science, what base are you thinking of? 2. Right? You want to do things in base 2, on, off. Computers work very nicely in base 2. Any fans of The Onion? Beautiful article years ago, Microsoft patents the 0 and the 1.
Yeah.
Then there's also jokes about working in base 1. All right, so we have pi is 3. Anybody know a better approximation for pi?
0.1.
No, as a fraction. 22/7. And then there's other approximations you can do. Anybody know other approximations? Uh, 355/113 is next. And so the question is, where do these come from? And how good of a job do they do? I'm going to show you a good way to approximate irrationals with rationals. I'm not going to show you a good way to approximate rationals with rationals. Why not? You don't need to approximate rationals with rationals. Here's a rational number. Can you find a good rational approximation to it? Yes. Yes, I can. This is called the mirror method. You just look at the number. That's your approximation. All right? And if you try to do anything other than that number, it's going to be bad. Right? So we're going to measure a rational approximation based on the number of digits of the denominator. So the more digits the denominator has, the more expensive it's going to be. And so if we use 22/7, this is 3.143, I think. 3.143. And what's pi supposed to be? Yeah, so that's not bad. If we do 355/113, I have to approximately, this is 3.1415929. And what is pi? 3.1415926.
27 technically.
So they sometimes put like a plus here, I think, to denote that I'm not sure, is the next digit higher?
5.
Although they've got a plus for the next one, so I don't know. We'll just do it like this. So basically 1, 2, 3, 4, 5, 6 digits that are correct, and the 7th digit we're very close. Over here, 2 digits correct, 3.1415, not too bad on the next one. So the interesting question is, how much better do your approximations get as you take more and more digits? How do you find these approximations? The next one is 103,993 over 33,102. And so, you can check and see just how many digits of accuracy this provides. So, where do these come from? Any thoughts as to what will be the key idea in finding the existence of good rational approximations? Pigeonhole principle, right? There's a theme to today's lecture. There's a reason why we're developing this tool. This tool can be used to solve real problems. And when you want to approximate numbers, You want to find good rational approximations. The smaller the denominator, the easier it is to work with them, and you want to get really good approximations. It turns out, if a number is too well approximated by a sequence of rationals, the number is transcendental. It is not the root of a polynomial of finite degree with integer coefficients. So this is one way to prove the existence of transcendental numbers, is you show that there are certain numbers that can be so well approximated by rationals that they can't be a calm irrational. They can't be solving a polynomial of finite degree. They have to be solving a polynomial of infinite degree. We sadly can't do this for the proof that pi and e are transcendental. Those proofs are painful and involve looking at some special functions, doing some very clever integration, and assuming that they are of an algebraic number, you then get that there exists an integer between 0 and 1. And as there are no integers between 0 and 1, you get a contradiction. If people are interested, we can definitely talk about stuff like that. So I want to show how you can use the pigeonhole principle. So here's so this is, so not surprisingly, this result is due to Dirichlet. We sometimes talk about Dirichlet's box principle. This is one of the big applications he had of stuff like this. So we'll assume alpha is irrational, and we want to write alpha minus p over q as small. Okay? It turns out, theorem, there exists infinitely many relatively prime p and q such that if alpha is irrational, then alpha minus p over q is less than equal to 1 over square root of 5 q squared. I will be lazy and I will prove this without the square root of 5. I'll just prove that you can do less than equal to 1 over q squared infinitely often. So that's really nice. So if you think about approximating with just 1 followed by zeros, that's approximating basically to within 1 over q. So the standard decimal approximation approach gives you 1 over q. This does much, much better. Now here is my question to you. Does anybody know what is the most irrational number in the world? And again, there are different ways of defining irrational. Any Isaac Asimov fans? He has a great story, Uniqueness is Where You Find It. I'll try to send that story for you. If somebody can remember to email me, that'd be great. Where basically I think a grad student wants to marry his advisor's daughter, and he's basically threatening to not only say no, but flunk him out of grad school unless he can solve the following problem. I am thinking of a unique element. And based on what you know about me, you should be able, in chemistry, you should be able to figure this out. And if you can, your life will be good. And if not, I will ruin your life. It's sometimes fun to be a professor and have grad students. But there are different notions of uniqueness. So when I say what is the most irrational number, I mean which is the irrational number that's the hardest to approximate with rationals? Which is the one where you do this well? And every other irrational number you can actually do better than this. There is one irrational number that is just a real pain. Anybody know? You've seen it in this class. The golden mean. So phi, which is 1 plus root 5 over 2, is the worst. So for all the talk about the beauty of the golden mean, in this sense, it's actually the worst. In this sense, it is the most irrational of all numbers. I think anybody have a guess as to what the second most irrational number is? After the golden mean?
Plus a constant?
I'm sorry, no. No, because you're absolutely correct. So we will look at things like mod 1 or 2 or something like that. And we will consider if they differ by an integer, they're the same number.
Root 2.
No. No. The golden mean is the worst. What do you think the second worst is? The silver mean. I think the silver mean is the second worst number. I'm not 100% sure, but I think the silver mean comes in second.
What is the silver mean?
I think it involves square root of 2. I know, but it's... Was the joke answer the silver meat? Yeah. No, but it's okay. It's sometimes called the silver ratio. Well, it may not be quite related to square root of 2. It does have a lot of 2's in the continued fraction expansion. Okay, so maybe it is. Maybe it is 1 plus. It might be 1 plus the square root of 2. Okay, so the silver mean might be 1 plus square root of 2. All right. So what I want to do is I want to do the box principle. So if we're doing the box principle, we need to look at pigeons. We need to look at boxes. So what we're going to do is we're going to let xn be n times alpha. And then we'll let yn be n alpha mod 1, because we really don't care about the integer parts. And so if we look at the interval 0, 1, we can break this up k over q, k plus 1 over q, all the way down to q over q. So each box has length 1 over q. This should remind you of our proof of the fundamental theorem of calculus. We just divided the interval. So if I start looking at these numbers will fall in different boxes, say. If two numbers are in the same box, how far apart can they be? At most 1 over big Q. So how many pigeons are going to be the YNs? Or the XNs that are equivalent. How many pigeons do you want? Q plus 1. So let 1 let's equal to n, let's equal to q plus 1. So the pigeons are the xn or the yn, and the boxes and then the boxes are the intervals k over q to k plus 1 over q. I guess technically we should do it, closed and half open. When we do it like this, we miss having the box at the point 1 at the end, but that's fine. It's a irrational number. It's never going to be at the end. So 2 in the same box. So we get n1 alpha mod 1 and n2 alpha mod 1 in the same box. So we can write this as n1 alpha minus m1, subtract off the integer part, minus n2 alpha minus m2. And how far apart must they be? At most 1 over big Q. So we can write this as n1 minus n2 alpha minus m1 minus m2 is thus equal to 1 over big Q, or alpha minus m1 minus m2 over n1 minus n2 is thus equal to 1 over n1 minus n2 times q. Okay? Now, which is larger, q or n1 minus n2? What's the farthest apart n1 and n2 could be? The n's are going from 1 to q plus 1. So what's the farthest apart they could be? Q. So this is going to be less than equal to 1 over n1 minus n2 squared. So we've just shown that there are two numbers p and q such that alpha minus p over q is less than equal to 1 over q squared. It would not be impressive to show that we could get alpha minus p over q to be less than equal to 1 over q. Just move in blocks of size q, and there's got to be a rational within 1 over q of it. But the fact that we can get to 1 over q squared is amazing. It's significantly better than you might expect. Okay? I am not getting the square root of 5. The square root of 5 is more advanced theory. And we'd have to delve a little bit into continued fractions. I really don't care enough to do it. Yes?
So is that actually less than or equal to n1 minus n2 squared, or is it less than or equal to q1 over q squared? Or am I just...
Well, n1 minus n2 is less than q. Which would you rather divide by, 5 or 50? Dividing by q is going to make things much, much smaller. So I'm replacing q with a smaller number, so that makes the fraction larger.
Right, okay.
I always have to play these games myself, and I always say, all right, let's let q be 50 and the other one be 5. If I divide by 50, that's going to make it much smaller than dividing by 5.
Gotcha, that makes sense.
And so the reason is, the square root of 5 is really not that important. What really matters is the dependence on q, as q grows. Now, there's one small subtlety that you need to finish the proof. I claimed that there were infinitely many. Well, as I keep doing q, what if I kept getting the same fraction every single time? But here's the thing. We know this is less than or equal to 1 over n1 minus n2 big Q. It's also less than or equal to 1 over big Q. So this is the small little technical part. Also, alpha minus n1 minus n2 over, m1 minus n2 over n1 minus n2. This is also less than or equal to 1 over q. I can't keep using the same fraction p over q again and again and again. The reason is the fraction p over q is a fixed distance away. If I kept using that same fraction, I could not eventually be less than 1 over q. As p over q is a fixed distance from alpha, cannot use infinitely often as we increase q. And that will finish the proof. So you just have to be very careful about that little technicality that maybe we keep generating the same damn fraction p over q again and again and again. So over here we initially replaced q with something smaller. Now we just drop the 1 over n1 minus n2 to show us that we can't keep getting the same thing again and again and again. So this is one of the most important applications of Dirichet's box principles. It tells you if you want to approximate an irrational number, you can do at least this well. And if people are interested, let me know. It's not that hard to prove that if you can approximate a number very well, it must be transcendental, and then we can actually construct transcendental numbers explicitly. So if people want to see that, just let me know. It leads to a beautiful theory called Liouville numbers. All right. For the last couple of minutes, there was a request which I had ignored already once, and I am not ignoring it twice. It was to talk about the fallacy of the hot hand. Is there such a thing as streaks of someone being lucky? And so what I want to do is I want to start off with a riddle to just get people primed. This is one of my favorite riddles. It seems surprising. When you see the solution and you see the right way to view the problem, it's not bad. And it turns out that this problem has enormous applications in the real world. So it's not just a, here's a math riddle for the sake of having a math riddle. This is a problem which in some sense is the basis of e-commerce. Okay? Do you want to do the violent or the non-violent version of the problem?
Oh.
For those of you who don't want to do the violent version, be careful where you sit. So we have 3 people. Okay? And what we're going to do is we have 2 types of hats. White hats and black hats. Okay? Each person randomly gets assigned a hat. Randomly and independently get a hat. And each person can see the other 2 people's hat, but not their own. Okay? The 3 people Fortunately, are mathematicians. They are the brightest possible people in the universe. And they are allowed to strategize before the game begins. Here's the rules. Everybody closes their eyes, the hats are placed down, and then they go 1, 2, 3, open your eyes. You have 5 seconds to look, and then at exactly 5 seconds, you must choose to speak or stay silent. If you speak, you must say either white or black. If everybody who speaks is correct, then everybody gets to live. And they get $1 million. If even one person speaks and is wrong, then they are all killed, and not just killed, but killed by watching Barney reruns followed by Jar Jar Binks interviews. It's going to be a painful death. It's not just death, okay?
What if no one speaks?
Yeah.
If no one speaks, then you don't get the money, but you don't die. So of course one strategy is to just have nobody speak. But you really want that $1 million. Can somebody give me a strategy where you're guaranteed to win half the time?
One person speaks randomly.
Good, and what do they say?
Doesn't matter.
If they say doesn't matter, they die. What should they say?
Black.
Black, okay. So one person says black, rest silent. You win 50% and you lose 50%. Can anybody give me another strategy that will win 50% of the time?
One person says white, rest silent.
Yes, that will also work. So we have 2 strategies that will do 50%. So the non-violent version of the game is if you win, you give me $1 million. If you lose, if you win, I give you $1 million. If you lose, you give me $1 million. Can you do better than 50%?
Wait, are there an amount of black hats and white
No. So each person has a 50-50 chance of having a white or black hat, independent of the others.
hats? Okay.
If there were a fixed number of hats, then that would change things.
Yeah.
But it's very important for this problem that the number of hats is fixed. Everybody gets 1 hat, and each hat is equally likely to be either color. So any thoughts on how to do better than 50%? Good. This will be something for you to think about for today's Wednesday, for Friday's class. Before you think about it, though, does it seem possible that the team can do better than 50%?
No.
Right. Why is it this a no?
So the only way you can give information to other people is by saying something.
Right.
And then you automatically give.
Right. So the only way to pass on information to people is to speak. And when you speak, you are right half the time and wrong half the time. Right? You should not, no matter what strategy you come up with, since your hat is randomly put on your head, you should not be able to be right more than half the time. So it seems like there should be no way of beating 50%. That said, how many people think there's a way to beat 50%? Yes. Yeah. This would almost surely not be a problem I would love, and I would not be saying things such as e-commerce is built around this problem if you can't do better than 50%. So there has to be a clever way of looking at this. Don't say it. Okay? You can email me if you see a clever way. If you want to play this with your friends, please play the non-lethal version. I don't want to get an email from public safety saying, Professor Miller, we caught your students playing the hat game. Could you please meet us at the morgue? Okay, do the non-lethal version. So I want you to think, can you break 50%? And again, we seem to have the following strange theorem, that when you speak, you can't be right more than half the time, so how can you do that? I'll leave you with one other problem. What's what's the best tower we have on campus? Like building that looks like a tower. Thompson? Thompson Chapel?
Sure.
Sure. All right, so I will let you in on a little secret. Back in the 60s and early 70s, there was a nuclear program at Williams. We have a small number of nuclear missiles that we can fire from Thompson. Okay? It requires 3 members of the faculty to agree. The range is not large, but it is enough to hit central Massachusetts. So if we need to destroy a certain school about 90 minutes from here, we can do so. But you need 3 faculty. Okay? So what we want to do is we want to give passwords to the faculty in such a way that any 3 of them can launch, but no 2 of them can launch. You need 3 faculty together to launch. Okay? Any 2 faculty cannot do this. And so the password is a polynomial f of x is ax squared plus bx plus c. That's a triple ABC. And so we need to assign information to the faculty in such a way that no matter which 3 faculty members you choose, they can determine A, B, and C. Is it possible somebody is given all of A, B, and C? No, why not?
Then they knew themselves.
They would be able to launch themselves. So one thing you could do is you could maybe have a polynomial of degree 12, and maybe the president has the ability to launch herself. That she knows enough information that if she decides to nuke Amherst, she can. And then maybe you give more information to, say, the provost and some of the deans, so that maybe the provost and 1 dean would be enough. And you could give different levels. Full professors get this much information. Visitors shouldn't be able to launch the missiles. So you agree that we can't give anybody 3 of A, B, and C. What if one person knows A and B?
Then you can't give out C at all?
Then you can't give out C at all. So if you only know one piece of information, so there'd be people who know A, people who know B, people who know C. Well, there'll be multiple people who know A. So if you have 2 of the people who know A, then there's no one you can put in to help them. So it seems like there is no way to pass out the information. So I claim that there is a way to pass out information so that any 3 professors can nuke Amherst. But no 2 professors can do so. You need all 3. So you need to think about how would you do something like this. Right? So these are just fun problem-solving things. This is a more interesting example of why we care about quadratic formulas and stuff like that. This will hopefully tie into some things you've seen before, but with a nice twist. So it all comes down to how do you convey information? And it's not always the way you think. All right.